Okay guys, I wanted to take you through the formaldehyde calculation that we did in class last week and show you how it's done using GaussView 6. So what you need in order to use GaussView 6, you need to log into one of the Macintoshes. I think we resolved the problems that we were having before. I guess we'll see this week. And once your account gets open, what you need to do is open the terminal application. And so if you don't see a terminal application here in the dock, you can get to it in a number of ways, depending upon what you do have. You'll at least have this Finder application here, which you can click. And then if you go to the Applications folder here on the right-hand side, and then scroll down to Utilities, you'll see the terminal application here, and what you need to do is to drag it down all the way to the dock and put it on there, and then you'll be able to open it from the dock from now on. And so I'm going to go ahead and close that, and then I'm going to open the terminal application, and then to start GaussView, I'll leave it down here, you type the letters GV for GaussView, and then enter or return, and it should start the application. You get a little splash screen here that goes away in a minute, and then there's a GaussView tips, and so each time you open the application, unless you check that box, what you're going to get here are just the tip of the day, so to speak, and you can take a look at those. Sometimes they'll make sense to you, other times you won't know what it's talking about. But as you learn more about Gaussian, then these will start to make more sense. I'm going to go ahead and close that here. You can access the help for GaussView right here, so you can learn all about it. It'll take you to a website where they have a couple of how-tos, and then they have the full menu here that you can go through. So this is a good resource. You'll probably be spending some time looking over the documentation as you try to do different things for your mini projects. So I'm going to go ahead and close the help, and what we're going to do is just go through the basics of GaussView. We'll build a simple molecule, formaldehyde, and then I'll take you through a calculation, and we'll just go through the major pieces of the output that you get for these types of jobs that we do. So you've got two windows here that are associated with GaussView. So this is the builder. It's the main Gaussian menu. You've got the menu items up here at the top, and then all these little buttons. They do different things. This blue box over here, this is where you build your molecule. And so what we're going to do is construct formaldehyde. There's actually a really easy way to do it, and that's just to use this this R group fragment where they've already got formaldehyde built in. I'm going to show you how to build formaldehyde from the bottom up. And so I'm going to go over here to this element fragment select item. And so we see here we've got methane. So by default it opens up to a tetrahedral arrangement around a carbon atom. We obviously want an sp2 type carbon. And so I'm going to click the button here. It'll open up this periodic table dialog. You can choose different atoms, okay, and then different bonding arrangements around that atom. We're going to go back to carbon here, and instead of the tetrahedral geometry, I'm going to choose this carbon trivalent geometry. So I'm going to select that. You see that the fragment here, the current fragment that I'm working with, has changed. And then I just click inside this blue field, and then it puts whatever's here, it puts it inside my new molecule window. Next, what we'll do, we want to add the oxygen atom, and so I'm going to go back to the periodic table. I'm going to choose oxygen. You could really get away with the oxygen atom or the double bonded oxygen. I'm just going to choose this one, and then I'm just going to click right here, and it's going to add the oxygen where I want it. Okay, so this is the formaldehyde molecule. You can do things, for example, if you make a right click in the, oops, I guess that's not what I want to do. If you make a mistake you can hit Control Z, or sorry, for the Macintoshes it would be Command Z, and that'll delete it. I believe if I hold down Control and then sort of right-click on the mouse, you get this dialog here, and you can do things like view the labels. So this carbon is atom number 1, this hydrogen is atom number 2, atom 3, the oxygen is atom 4. Again, I made a little error, so I'm just going to delete that fragment. I'm going to hold the control button down, and then right-click, and I can add the atomic symbols to just remind me what atoms I'm dealing with, and so you can see that there. The mouse wheel allows you to zoom in and out, as you see there, so you can change your perspective by holding the Shift key down and then clicking the left mouse side. You can translate the fragment around. If you just click anywhere here in the blue space and hold it down, it allows you to rotate the structure around like this. If you wanted to spin the structure, I believe what you need to do is to hold the shift control combination, and then let's see, no, it's the command. If you hold the command button down and then the left mouse button, you hold the left mouse button at the same time, you can rotate the structure around like that. Anyway, that's just sort of navigating around the molecule. You'll get a feel for it once you play around with the controls. Combinations of shift and command and the mouse button allow you to do different things here in the field. You can also access that kind of thing through the menu item. So I could turn the labels off. I could turn the symbols off. I can hide the bonds if I need to do that for some reason. You don't really need to do that, but this kind of thing. So you can play around with the view, and all that stuff is here. It's here in the in the Gaussian help, explained in narrative form. Oftentimes you might want to center the molecule before you get going, and so there's a button up here. Let's see if I can find it. It looks like I need to expand my view here, so I've got all the buttons here. This little button here says center the molecule in view. You'll see that it'll center the molecule in the frame that you have here. So we've got our formaldehyde. What we're going to do next is it gives you a little report here, how many atoms you have, how many electrons, what the current charge is, and then what the spin multiplicity is. We've talked about that in the other videos that we've taken a look at. And so let's just launch the calculation here using GaussView. So you can just choose the calculate menu item, okay, and then choose this Gaussian calculation setup. And it's going to pull up another dialog here. And this is where you choose all of the keywords for the Gaussian job. So we want to do, for this calculation, I'm going to go ahead and do an optimization frequency job. And then once you choose that, there's some other options that you can go through. We're just going to use all of the default settings. That's usually what you want, just depending upon what you want to calculate. And so sometimes we're going to play around with these, but for this calculation, we don't really need to. The next thing you typically want to choose is the method, the model chemistry that you're planning on using. By default, Gaussian will try to calculate the ground electronic state using the Hartree-Fock method with a modest 321G basis set. It's useful if you have medium-sized molecules, so that's a pretty good one to use if you want to start off with that. Since this is a very small molecule, we can actually get away with a much more accurate method in our initial calculations. So I'm going to go down here and I'm going to choose one of the density functional theory methods. Keep the default spin, and then here, this is where you choose different flavors of DFT methods. And the one that we're typically going to use, the one that's recommended in the exploring chemistry with electronic structure methods, is this APFD. The A, the P, and the F are the first letters of the last names of the authors of this density functional theory method, and then the D, I believe it stands for dispersion. Since it's a small molecule, we can bump up the basis set, and so I'm going to go down here and I'm going to select one of these triple zeta basis sets from the Popel set. So this 6311G, it's a good sized basis set. We're going to go ahead and add some diffuse functions here for the heavy atoms, so for the carbons and the oxygen. So we'll be including diffuse basis functions that we've talked about in a previous video. And I'm going to add some polarization functions such that the electronic structure that we determine is fairly flexible. And so we'll pick the 2D. That's going to add a pair of D or a pair of sets of D orbitals to each of the heavy atoms. And then for the hydrogen atoms, we're going to add some extra P orbitals to increase the flexibility of the basis set. We are interested in the charge, but if you were interested in a cation, you can just dial in whatever charge you want, or you could do an anion. Again, we're going to do the charge here. And then for our calculation, we're going to be interested in the singlet state, where all of the electrons, all of the 16 electrons are paired. That is, there's an up electron paired with each down electron. As we've discussed previously, you do have to specify the spin multiplicity because different spin multiplicities would correspond to different electronic states. So if you wanted to then unpair the electrons or allow the electrons to become unpaired, you could do that as well, and this will force that to occur. We, however, based upon prior experience, know that the ground state of formaldehyde is a singlet, and so we're just going to keep it selected at the singlet. There's all sorts of keywords that you can add depending upon what job that you want to do, and then those keywords are all described in the Gaussian documentation. For this simple job that we're doing, we don't really need to add any additional keywords. Here we can add a title, so we'll just say, ground state optimization and frequency calculation for formaldehyde. You can really put anything you want there. It's helpful to put in something reflective of what your intentions were with the job. That way when you look at these output files later and you've done all sorts of jobs, you know what that calculation did. So you can just leave little notes to yourself, and you can put as much text as you want here or as little as you want. We really don't need to specify anything for the link 0 options for this type of job. This is how you control how the job functions in terms of what files it uses and their file names. You can also play around with the memory limits and the number of processors that are allowed for the job. We really don't need to get into that for this particular job. So we're just going to use the default options here for this tab. We will occasionally be using the general tab, but for our purposes here, we can just stick with the default settings. But you can add additional things. You can compute different quantities. You just add that in. You'll notice that it added a keyword into the route section. I'm going to go ahead and turn it off since we don't need it. Usually the default guess strategy works. Occasionally we'll need to use this. It really just depends upon the job. For some molecules you do need to select these options. For others you don't. It just kind of depends. Again, the population and the solvation tabs, we don't need to worry about those. I'll take us through a whole, we'll have a whole 2 weeks on playing around with different solvations. So this is where you would add the effects of a solvent. We're just going to do a gas phase calculation here, so we won't include a model for the solvent, but we'll go through that sometime in the future. The little preview button here, it shows you what the input file looks like. And so We've discussed this before. You know, there's some link 0 commands here. This is the route line. This is the title. This is the this larger section here is the molecular specifications, and so it's a charge of 0, spin multiplicity of 1 for a singlet, and then by default it's putting the molecular geometry in using Cartesian coordinates. So this is the x position of the atoms, the y position, and the z position. This little section down here, just refers to this connectivity. So this is which atoms are connected to which. And so we see that atom 1 is connected to atom 2 with a single bond. Atom 1 is connected to atom 3 with a single bond. Atom 1 is connected to atom 4, which is the oxygen with a double bond. And so that's what this section is. It just kind of tells Gaussian how the molecules how the atoms are connected together in the molecule. So this is the input file for the Gaussian calculation. And what I'm going to do is, now that I'm ready to submit the job, I'm just going to go here and use the submit button. And then it says you must save the Gaussian input file before you submit. Would you like to save now? You just choose save. And then you're going to get a file selector dialog. Generally speaking, we don't want to save it here. This is the applications folder. And so you'll want to use, you want to put it somewhere in your home directory or on the desktop. Just depends on where you want to put it. I'm just going to choose my home directory here, and I'm gonna create a directory here that I'm just gonna call. Let's see. I want to make sure that that's selected, and then I want to create a new folder here, which I'm just going to call Gaussian. And so I'll click that, and then I'm going to give the input file a name. I'm going to call it just form for formaldehyde, and then you hit save. And then now you're ready to submit the job. And then since this job is short, we don't really have to wait very long. So I'm just going to have it notify me when the job is finished. I'll just choose yes. So it's submitted the job. And now we're just going to have to wait a few seconds for this job to complete, and then Gaussian's going to pop up a dialog telling us that the job is done and give us the opportunity to open up the output files. And so this shouldn't take too long. We did choose a pretty good basis set, and so it will take a few seconds to optimize the structure, compute the vibrational frequencies, and then give us the output. You can actually monitor the different jobs, I believe, by, well, it popped up before I had a chance to do it. So you can go here and you can actually monitor which jobs are done or which jobs are running. And so we are going to go ahead and let's just open we have a choice. We can either open the checkpoint file, which has a lot more information on it, or we can open the log file. I'm going to go ahead and just open the log file instead. And so I want to show you what's in the log file. This is a binary file. It's not human readable, but this one we can actually open up the raw file and take a look at what's in there. So I'm just going to open up that file. You'll notice it spit out a new window here. So this was our initial file. Notice it's the GJF. That's the input file. And then what we're looking at here, this is the log file. So this is the final file from the job. So I'm gonna go ahead and close the input file so we don't get confused. And then what I wanted to do was just to show you a few things about the output that you get from a Gaussian job. So what we'll do next is I'm going to go to the results tab, and first we'll just look at the summary. Okay, so the summary of the job here. It tells us what file we're looking at, what type of calculation was completed. So this is the frequency portion of the job. It spits back the method that we used, the basis set, all of the details that we plugged in, the fact that we didn't use a solvent, and then after that comes the electronic energy evaluated in units of Hartrees. Because we did a frequency calculation, it has information about the first derivative of the energy with respect to the different ways in which the molecule can move. because we did a frequency calculation. It gives us some information about the frequency job and how it completed. We're going to talk in more detail about what this means in a future video. And then you'll see here it's giving us some information about the electronic structure. It tells us the magnitude of the dipole moment. It tells us the polarizability of the molecule. And in this case, it looks like we didn't quite get to a C2V point group, but we could probably improve the result a little bit if we added symmetry to the calculation. In any case, what I'm going to do next is to go back to the results, and I'm going to open up the charge distribution summary. And so here, what you see is this is one of the items that's calculated by in each Gaussian calculation. It performs what's called a Mulliken charge analysis, and it performs different types of analyses. So the ones that are available to right now are the Mulliken or this APT population analysis. And what the population analyses do is they employ different methods for analyzing the electronic structure of the molecule and assigning partial charges to the atoms. And so we can turn those charges on by showing the numbers. And so what we see here is that the oxygen atom, as you would expect, because it's electronegative, it's the more electronegative atom in the molecule. It takes on a slightly negative charge in this analysis, and the carbon and the hydrogens are more electropositive, with the hydrogens being more electropositive than the carbon. You can do things like color the atoms by their charge. So it's using this color bar here to assign the negative charge, and then the positive charges are assigned here. And that can be useful for attempting to visualize how charge is distributed through the molecule. And there's other ways of doing that as well. I'm going to go ahead and turn those quantities off. And what I'll go to next here is displaying the dipole moment of the molecule. So we talked about the dipole moment in a previous video. Here's how you display it using GaussView. You just click this button, and I'm going to zoom out a little bit, and it shows you here that in the Gaussian calculation, or in the GaussView window here, it shows the dipole moment as a vector pointing from the center of charge of the molecule, which is right here, and it shows it pointing towards towards the positive charges. And so you may recall from general chemistry that by convention we typically draw the dipole moment from the center of positive charge as an arrow pointing towards the center of negative charge. In GaussView, it's actually reversed. They have it pointing from the negative. They have it pointing in the opposite direction, and so it just depends on what your convention is for plotting that vector. This is essentially the negative of the definition that you're used to in chemistry. Let's see here, and here's the magnitude of it. So the dipole moment has 0 component along the x-axis, 0 component along the y-axis, and it's pointing along, or 0 component along the z-axis, and it's pointing along the y-axis. Okay, so this is displaying the dipole moment. So formaldehyde is a polar molecule. I'm going to go ahead and close the charge distribution dialog, and let's see, what did I want to do next? Oh, we wanted to go through. Yeah, let's go ahead and I'm going to go ahead and close this. We're going to open it back up again in a little bit, but I was going to take you through the molecular orbitals. I think I do want to turn off the dipole moment though. So go back to the charge distribution, and I'll just turn that arrow off. Next, what we want to do, we're going to use the log file. It's actually a little bit more efficient to use the checkpoint file, and so for this next operation. So I'm going to just kind of put this guy right down here, and I'm going to open up, show you how to open a file, open, and we're in my home directory here. It looks like it looks like when I saved the file I missed my actual Gaussian directory. That's okay. I can move those later. And I'm going to open up the checkpoint file like so. And it's the same, most of it's the same. When you go to the results, okay, you're going to get all of the same values here. But the checkpoint file stores the molecular orbitals in that file, whereas if we were to do this using the log file, I think we might have to generate them. Is that true? It really depends on what you saved in the log file. Usually it's a bit more efficient to use the checkpoint file, as I recall. So I'm just going to minimize this real quick, and we'll just focus on this file here. And this window here, this looks like a p orbital. This is the molecular orbital editor. You can use that to generate different molecular orbitals and view them. And so what you see here, this is a listing of all of the molecular orbitals that were calculated. You see that the lower set here, these are the occupied molecular orbitals. And then these up here, these are the unoccupied or virtual molecular orbitals. Very often, one is interested in knowing information about the highest occupied molecular orbital, or the HOMO, or you're interested in knowing about the lowest energy unoccupied molecular orbital. So this is the index of molecular orbitals here. This box shows you which ones are occupied and which ones are not. You see that the first 8 orbitals are each occupied and the electrons are paired. And then this number here, this is the energy of the molecular orbitals. So these are the lowest energy molecular orbitals, the lower energy occupied molecular orbitals, and this is the highest one. So what we'll do next is we will select, we'll go to the visualization tab here because we want to visualize these orbitals. And what I'm going to do is, since it's already selected for highlighted, you can choose different ones. The ones that are highlighted, that's great. Those are the HOMO and LUMO, or you could just select that outright and it's the same thing. It's the same 2 orbitals, orbital 8 and orbital 9. And I'm going to update my list here. You'll see what it's doing here. It's generating the molecular orbital cubes for me. And so now you see that in this box here, I've got these boxes here that I can select. And so what you're looking at here, this is the highest occupied molecular orbital for formaldehyde. Okay. It has this sort of 4-lobed structure, whereas this one here, it has a different structure. And to help visualize it relative to the atoms, you can, let's see, I believe hit Control right-click. You can change the view here by going down to display format, clicking that, and then you can adjust the surface of that's displayed here for the molecular orbital. So right now it's displayed as a solid surface. You can view it as a transparent surface, and it makes it a little bit easier to see what the atoms are doing. And so we'll hit OK for that. And so this way you can see that the lobes here, they are perpendicular to the plane of the molecule. The type of molecular orbital that we're looking at here in the LUMO, this would be an antibonding orbital. It would be an antibonding P orbital between carbon and oxygen. And it's antibonding because it has a node between the 2 atoms where the wave function, this molecular orbital wave function, goes to 0. And then it's a pi type molecular orbital because you see the nodal plane that runs through, that runs across this way. The HOMO has a different character. Okay, this is really a non-bonding orbital. I believe what we have here, this is essentially, while there is some contribution from the carbons and the hydrogens, the bulk of the contribution is actually coming from the oxygen. This would be a lone pair. The electrons in this molecular orbital, we would classify them as a non-bonding set of lone pair of electrons on this oxygen atom. Let's see here. Oh, for fun, I'm going to go ahead and visualize a few more of these orbitals. Let's go ahead and do the lowest two and see what's the nature of those of the electrons in those lowest energy orbitals. So I'll update my list here. Okay, so we've added these two. So if I select here, this lowest one, you'll notice that the orbital is exclusively located on the oxygen atom, and so this is essentially core electrons on the oxygen atom. If we look at this one here, these are essentially core electrons on the carbon. I'm going to go ahead and add a few more. I'll just add the rest of the molecular orbitals to the list. It'll take a little bit longer to generate them all, but not too long. And we'll go back to this third orbital. This one's hard to well, it's not that hard to classify. This orbital represents a sigma type bonding orbital between oxygen and carbon. Okay, so it's part of the double bond here. Let's look at this one. This one, I would classify this as carbon-hydrogen single bond, and it does have some contribution coming from the oxygen atom, but it's a sigma type bonding between the two, between the carbon and the hydrogen here, and this carbon and the hydrogen. This guy here, let's see, this would be additional electrons that are also participating in the bonding between, let's see, how would I classify this? This one's a hard one to classify. I think it would be a combination of both lone pair electrons on the oxygen and carbon hydrogen single bonding. Let's see. This would be another primarily lone pair electrons on oxygen. We see that we have this, and it would be a p-type of orbital. So these would be electrons occupying a p-type orbital on the oxygen. Here we get one that's a little bit more obvious. This is pi-type bonding between the oxygen and the hydrogen atom. We've already looked at these guys. This was the antibonding pi orbital. I'm going to go ahead and add just a few here just to see if we can catch an antibonding sigma type orbital. We may or may not. It could have been any of these. So here we're getting into some really weird looking orbitals. This is just due to the fact that we have so many basis functions in the molecule. We're capturing what are referred to as Rydberg type orbitals, which are essentially they're not occupied by electrons, and so they're essentially states where the electron, or they're essentially orbitals where the electrons would be very far from any of the nuclei. Let's see if I can make any sense out of that. That looks pretty Rydberg-like. No, I'm not. These probably aren't going to have much sense to them. So I'm just going to stop trying to visualize them. What this emphasizes, like some of these ones that are very hard to classify, this one, even this one to some extent, this guy here, certainly these higher energy unoccupied orbitals. What they demonstrate is that the molecular orbitals that we're calculating here, while they do have some physical meaning, they are really they also have a more abstract meaning in the sense that there's different strategies for computing the molecular orbitals that are equally good. And so these are just referred to as the canonical molecular orbitals. That is the common way of calculating the molecular orbitals. But there are other equivalent ways. And so sometimes we can generate a physical interpretation of the orbitals fairly easily. For example, when we're looking at the antibonding pi orbital or the pi bonding orbital, it's very obvious what type of orbital it is, but very often you'll also have orbitals that it's hard to make heads or tails of. Now there are different types of population analyses that you can do. The one that comes to mind is the so-called natural bond orbital analysis, which essentially reorganizes the molecular orbitals into a way that looks a lot more like what you would have learned in general chemistry. And so that's an analysis that we're going to do at some point, probably in a future video. I could have done it for this formaldehyde. We may, in fact, do it for formaldehyde just for comparison's sake. In any case, this is how you generate the molecular orbitals. If you want to capture an image, so for example, if you wanted to include one of these orbitals in your mini report, you can, let me square it up a little bit. What you can do, you kind of align it the way you want. You don't, for these mini reports, you don't need to do it perfect. It's not like it's going to a journal or anything like that. So this is showing the pi bond, the pi bonding between the two atoms. What you can do then is hit, I believe it was Control right click, and you can save the image to a file. You can save it. There's different file types, I think, that you can use, if I'm not mistaken. And so we'll just hit, I was hoping to actually change the name of it. File save options. You can change the background if you want. You could make it, you can make the background white. It's up to you. File list. No, I'm just going to hit save. And then I'm going to use my finder here. Let's see, where did we store this guy? So it's right here. So you see that this TIF file, you could then drag this into a, you can edit it, and then you could drag this into a Word document or something like that. For some of your mini reports, you might be examining the molecular orbitals, depending on the application that you're working on, and this is how you could save those into a figure format, so you can later incorporate them into your document. You can also do that kind of thing here in the window, and so I'm just going to show you an alternate approach to generating the molecular orbitals. This view here in the molecular orbital editor is nice because it shows you the molecular orbital energies. Alternatively, you can not open that and then go to the results and look at the surfaces and contours. And so here what we'll look at, rather than looking at the molecular orbital, what we're going to do, which are stored here, so these are each of the orbitals that you could then generate, and just to highlight that, I could take this, I believe this was the HOMO, if I'm not mistaken, this one here. So you see that the cube is already available to us. We can just do a new surface, and then it'll show it to us here. And so you can then use this dialog, and if you wanted to take a different picture, you could use the camera view here, this little camera save picture, and then the file saving dialog is a little better because you could choose the name, and you could write it as HOMO save, and then you'll see that file was created as well. Let's see. I guess I wanted to show you another surface. So what I'm going to do now is select the surface that we currently have, and I'm going to hide it. No, remove surface, so that, oops. We will do hide surface, so that took the molecular orbital surface away. I'm going to go up here to cube actions, and we're going to make a new cube. So a new surface is what we're going to generate. And instead of doing a molecular orbital, I'm going to do the total electron density. Okay? And just select SCF, and then we'll hit OK. It'll generate that, and then that surface will then appear momentarily, it looks like, in the, it's supposed to, eventually it should make its way into the available surfaces. No, what I need to do, here it is. So it's in the cubes available. So then you select that cube, okay? And so what we're going to do is then generate the surface from that cube. So I'm sorry, I was waiting for it to appear here. I was mistaken. It appears here in the available cubes. You select that, and then you do new surface, and then what it's done now is it's added the new surface here. So this is the total charge density for the molecule. And just to make things a little bit easier to see, again, I'm going to hit Control right click, no, Command right click, gosh. For some reason I'm not getting that dialog to come up. Maybe I need to, there it goes. So I hit Control right click, go back down here to the view, display format. You could also, if you're having trouble like I am getting that dialog to show up, you can also just go up here to view and then do display format, and then we can then change the visibility of the surface. So here it's being displayed as a solid. I can make it transparent, or I can make it mesh. Mesh is a little, I mean, it's kind of cool looking, but it's usually more distracting after a while. And so the transparent works pretty good. And so I'm going to go ahead and select OK. And so you can see where the molecule is relative to the surface. So this is the charge density of the molecule, one particular ISO value of that charge density. And so it gives you a sense of roughly how big the molecule is, in terms of the electron distribution. And it also gives you a little bit about the shape of the electron distribution. Certainly it's not symmetric, and so this is a polar molecule. And you might want to save that right here. So you just use this button to save the SCF density, and then you can include that into your mini reports. So that's what I wanted to show you at this point for the electronic structure. Well, let's see. I think there's one more thing I wanted to show you. Let's make one more cube, new cube. Let's make the electrostatic potential. So these usually are kind of neat. So I'm going to hit OK. And so that surface has been generated, and now I'm going to hide this surface, and I'm going to make a new mapped surface. So maybe what I want to do is actually, I don't want to hide that. Let me show that surface, and then now what I'm going to do is I'm going to map the electrostatic density on that SCF, or the electrostatic potential, onto the SCF density. And so we'll hit OK. Oh, I think I did it wrong. We'll delete that surface. Remove surface. Let's see. I'm trying to remember the order of doing this. No, I think I'm just doing the same thing. Me let me highlight that and keep that one, and then do new mapped surface there. Oh, I bet well, maybe I know what happened now. Let's see, use electron density from total. I don't think that's right. Let me delete that again. Remove surface. Yeah. Okay, so believe it is, click that. No. Yes, electrostatic potential. And then choose the surface. And then do new mapped surface. Oh, I think I got it now. Okay, choose the SCF density and then do new mapped surface and then choose the electrostatic potential. That's how you do it. Okay, so what we're going to do, we select the surface, the cube that we want to make the surface here, and that's going to be the electron density. And then what we're going to do when we do the new mapped surface is we're going to choose the electrostatic potential. Scroll down, choose that. That's what I wanted. Okay, so the surface that you see here, it's the same electrostatic, it's the same charge density that we were looking at before, but now what it's showing you is the electric potential around at different points along the surface. And as you'd expect, in the region around the oxygen atom, the electrostatic potential of the molecule is negative, and then around the carbon and hydrogen end, the electrostatic potential that a test charge would feel is positive. Okay, so this gives you a sense of how is the electron density distributed, and then what is the electrostatic potential at different points around the molecule. And so these are kind of attractive figures that you can make to highlight the charge distribution within the molecule, and also how whether it's asymmetric and you have an electronegative end or an electropositive end. This can be useful information, useful visual information for trying to understand the electronic structure of the molecule. So sorry it took me so long to remember the order in which you do that, and I'm happy to help you in class to make your electrostatic potential maps look cool like this. So I'm going to go ahead and just close the close this molecular orbital results section, and let's see. Well, I guess I should have. I'm going to go ahead and turn off that surface. So I'm going to highlight the one that's currently being shown. I'm going to do hide surface. And then next I wanted to move on to the other parts of the results. And so we did an optimization calculation. This is the checkpoint file. I'm going to go back to the log file at this point. So highlight the log file, and then I'm going to choose, I don't think I didn't include the different optimization steps, so I'm going to skip that. And so it really doesn't matter if I use the log file or the checkpoint file at this point. What I'm going to do is just remind you about the ruler, so the inquire button that allows you to do measurements on the molecule. So for example, what's the bond length between carbon and oxygen? So that bond length is 1.19721 angstroms. If you choose 3 atoms, these 3 here, it'll tell you what the bond angle is. We don't have a good dihedral angle in here, but you need to choose 4 atoms to tell you what the dihedral is. You can choose it. Okay, so this kind of this funny dihedral angle tells us that the molecule is planar. Go ahead and turn that off. And then I wanted to show you in the results section, since this was we included a frequency calculation in this job. You can go to the vibrations results section, click that, And here it gives you another dialog where you can analyze the different vibrational modes of the molecule. And we're going to spend a whole unit talking about the results of frequency calculations, but just for now I just wanted to show you kind of the basics of it. So here we see that this molecule has 6 unique vibrational degrees of freedom, and these are the frequencies of those vibrations. This column here tells you whether or not those normal modes of vibration are infrared active. You can do things like animate the vibrational modes to characterize them. So we see this kind of bending motion in the molecule, this sort of wagging of the hydrogens. As you start going up in frequency, here we have another bending motion. Here, this one is in plane. That is, the molecule remains planar, somewhat asymmetric. Here is a symmetric bend. I guess you'd call this the scissoring motion. This is primarily carbon-oxygen stretching. So this is the carbonyl stretch. You know, that would be a big prominent peak in the infrared spectrum. It's a little bit exaggerated here, of course, and you can, if you don't like that, you can turn this on. No, let me go back to 0 here. What I wanted to do was to scale the amplitude of the, if you want something a little bit more muted, not so dramatic, you can affect that. That's just the display of the normal mode. Here's carbon hydrogen stretching out in the this is the symmetric stretch, and then here's the asymmetric stretch. And you can then, let's see, you can look at the spectrum, the predicted spectrum for the gas phase molecule. Okay, so this is what Gaussian says the spectrum should look like, and then you can correlate, by looking at it. You can, so let's see, here was the carbonyl stretch. I selected that. So here you can watch the motion, and then this would be the big peak in the infrared spectrum, and you can find the other ones as well. And so if you happen to have a gas phase infrared spectrum of formaldehyde, you could then use this result to identify the different types of vibrations that you see in the spectrum. And so that's something that we're going to explore in detail. And you can play around with the options of all of these plots and so forth, and we'll do that explicitly when we get to that unit on frequency calculations. So I think I've showcased a lot of the major features. It's really just meant to be a demonstration of the types of things that you can do in GaussView, using the results of your Gaussian calculation. And as we go throughout the rest of the course, we're going to explore in more detail each of these different types of calculations, and then you're going to get some experience designing your own and analyzing the jobs yourself. So I'm just going to go ahead and shut it down here. Just go to GaussView quit. The files should be saved on wherever you saved them. And I'm just going to go ahead and stop the video right here.